calculations worksheet. And if you look to the first video, I want you to notice something because I really screwed up on the formula here. I accidentally forgot to type in this T right here in the change in displacement formula. So ignore the first video and the first formulas you wrote down in class and use this one. And go ahead and stop the video right now if you need to get that, have some time to write that down. Before we get into those formulas, though, let's go ahead and take a look at the graph that's at the very, very top of the motion calculations worksheet. And if you were to look at a velocity over time graph, or what I call an acceleration graph, if you remember in math class, we were talking about slope, and in math, for some reason, they use M for slope. And we said it was rise over run, or we also said it was the change in Y over the change in X. Well, on this particular graph right here, we have the velocity on the y-axis, so the change in velocity is on the y-axis, the change in time is on the x-axis, so that means the slope is equal to velocity divided by time, which we just said the other day was acceleration. So that means that slope and acceleration are the same thing. So if you're having a sloped line like this line would represent the acceleration. Well, what I want to talk about right now is how you can get the distance on this graph as well. And so I'm going to change this, instead of making it a slope line for right now, I'm just going to change it to a straight line. Okay? So that means that this person would be moving at a constant speed. They're not stopped, they're just moving at a constant speed. So the acceleration in this case equals 0 because there's no slope. Well, if you notice, this makes a rectangle. And if I want you to find the area of this rectangle, wouldn't we go length times width? Well, if you look at the triangle here, the length of this particular triangle is the velocity, and the width of this particular, I keep saying triangle, my fault, rectangle, the length is the velocity, the width is time, and I gave you that old right triangle that I told you to use the other day, that velocity equals distance over time. So if you take the distance equals velocity times time, and you look at velocity times time is the same thing as length times width, and length times width is the same thing as area. If you sort of put all that together, let's look what we got here. Area equals length times width. Distance equals velocity times time. So that means that you can say that the area and the distance are equal to each other. So whenever you have a velocity over time graph, we're just going to find the integral, or the area under the curve, and that's going to give you the distance. Well, if you had a triangle, it would be just as easy. But now, instead of doing length times width, if your acceleration went up like this, you'd find the area under a triangle, and a triangle is 1/2 length times width. So let's look at this graph over here. Bring this down. It wants to know the distance between the 0 and the 5 second mark. Well, if you notice, this is a triangle. Okay? So I'm just going to use 1/2 base times height. Then it says, what's the distance between the 5 and the 10 second? Well, that is a rectangle, so you do base times height. Now the third one's a little tricky because you have it's either a trapezoid or something along this, something like that. So I'm going to divide this into a triangle for the top part and a rectangle for the bottom part, and add those two things together. So it gets pretty easy if you just look at the area of that graph. Now I want to give you some example problems for how to do the motion calculation problems, the rest of them. And I handed out this little in-class motion calculations. It says difficult ones on the side there. I'm not going to do them all. I'm just going to give you some examples of what to do here. In fact, I'm going to start with, let's start with number 3. And the process I'm going to use for every one of these equations is I'm going to write down everything that's given to me. So let's just look at number 3 real quick. It says a car moves at 10 meters per second. Well, as soon as I see 10 meters per second, I'm going to write that down as my velocity. So I know that my velocity is 10 meters per second. And it coasts up the hill at a uniform acceleration of 2.5 meters per second. probably should be negative since it's slowing down, but we'll get to that a little bit later. It says how far, so I'm looking for distance, has it traveled after 5 seconds? Oops, should be a 5 right there. So what we're going to do here is we're going to look at this particular formula, and I want to see which one of these I should use. So I'm going to come up here, and let's look at the first one here. The first one has a VF, a VO, an A, and a T. Well, it has no distance in it, so therefore I'm not going to use that one right now. If you look at the second one down, it has a D in it, so I'm good there. It has a V and a T, so I'm good there. It has an A in it and a T, so I'm good there. So the second one's the one I'm going to use. Now, I can't use the last one because I don't know the T, or it doesn't have a T in it, okay? So that means the last one here is out. So let's use the second one and just get our answer from there. So I'm going to take change in distance equals the original velocity times time. And once again, that's where I screwed up on the first video, because I forgot to put in that T, and 1/2 AT squared. So now I come over here and start plugging in all my numbers. So the change in distance, the original velocity was 10. It moved that far for 5 seconds. I should put in my units, but we'll do that a little bit. I'm running out of room here. I'm going to put in the 0.5. The acceleration was 2.5, and it's negative since it's slowing down. And then I'm going to put in my time of 5 seconds here. And so let's figure out what the answer is. And so the first part's going to be naturally 50. The next part's going to be a negative 6.25. And then your final answer is going to end up being 43.75, oops, that's a 75 meters. Okay, let's do a tougher one. Let's do number 4 right now. We're going to use the same process. I'm just going to read all the numbers here. So runner travels 100 meters. Well, 100 meters is my distance, while being accelerated uniformly from rest. Now be careful with words like that. From rest means the beginning velocity was 0. At a rate of 2 meters per second squared. Well, meters per second squared is not velocity. Meters per second squared is acceleration. So I'm going to put in acceleration there. And it says, what's the final velocity? So now I have to find a formula that has all these in it. Well, the first one doesn't have distance, so that gets rid of that. The next one doesn't have final velocity, so I can get rid of that one. So that means I must use the third one. And so I'm going to start right there. So let's come over here. Sorry about that. I'm going to put in VF squared equals VO squared plus 2AD. From there, you just plug and chug. So let's, VF squared equals VO is 0. 0 squared, that's easy. 2 times 2 times the distance of 100 means that VF squared is 400. But I'm not looking for VF squared. I'm looking for VF. So I'm going to take the square root of both sides. And that gives you 20 meters per second. Now I want to take a gander at number 6. Number 6 says, remember, we're doing the same process. I'm just going to write down the letters and the numbers. A rock 2 meters above the surface. So my distance is 2 meters. That's going to be my starting distance. It's 2 meters above the surface of the moon, where the gravitational acceleration is 1.62. So the acceleration due to gravity is going to be 1.62. Now, since gravity is going to pull down, I'm going to make that negative 1.62. And it says how much time, so I'm looking for t, does it take for the feather. Now, I don't know where the feather came from, so I guess I turned a rock into a feather. But on the moon, it makes no difference because there's no air, so a rock and the feather will hit at the same time. But does it take to hit the surface? Well, actually, I gave you something here. There's two things I gave you that aren't in the problem. And that's the fact, if it's going to hit the surface, that means that the final distance is 0, because the surface would be 0 meters above the ground. And also, the starting velocity. You actually know VO because the rock, before it starts to drop, has a velocity of 0. So now I got to find a formula that has all these in it. And I can't use the first one because I don't know the final velocity, so I'm going to get rid of that one. The second one is a possibility because I have the D, I have the V and the T, and the A and the T, so that looks like a really, really, really good one there. And the last one I can't use because, once again, I don't have the final velocity, so I get rid of that one. So let's use this big old long equation here of delta D equals VOT plus 1/2 AT squared. Well, my change in velocity is going to be the final velocity, which is, change in distance is going to be the final distance, which is 0, minus the initial distance, which is 2. The original velocity was 0, and the time I don't know, but I don't have to care because it's 0, plus 1/2. The acceleration is negative 1.62 because it's going down. And then the time is what I'm trying to find out. And so that means that -2 equals 1/2 negative 1.62 t squared. So I'm going to divide both sides by 1/2 and also divide both sides by 1.62. Negative 1.62. These will now cancel out, and I'm left with t squared equals -2 meters over 0.5, 1.62 meters per second squared. So let's find out what that is. So now, if you just look at the left-hand side, I got t squared equals 2.469-ish meters over meters per second squared. Well, the meters are going to cancel out here. And I'm going to take the square root of both sides, because I don't want to find t squared, I want to find t. So the square root of 2.46 gives you 1.57, and the square root of second squared is seconds. And so that is my answer. I want to do a very, very challenging one, because this is one that you haven't done before. That's number 2. I should have made that one last. But it says determine the displacement. So I'm actually looking for D here. That's what I'm going to be trying to find, or the delta D, of a boat that is uniformly accelerated from 20 meters per second. Now, it seems like I just gave you acceleration, but I didn't. I actually gave you the initial velocity, because meters per second is velocity. And it goes to 30 meters per second, so my final velocity is 30. And it does this in 10 seconds. Well, that was good. So put down 2 T's. Yeah. All right. So I got the 10 seconds here. So what I got to do is I got to find a formula that has all those in it. Well, the first one doesn't have a D in it, so I can't use that one right off. The second one has an A in it, so I can't do that one. And the last one has an A in it, so I can't do that. So, well, that just bites a biscuit here, because I don't know which one to use. So what I have to do is I've got to find a formula that I can use to solve for one of the variables, and then put that variable back in a second formula. Well, what the heck does that mean? Let's take a gander. I'm going to start with what I don't know. So if you notice, I'm looking for D. And this formula right here solves for D. But if you remember, it has an A in it, and I didn't have the A. So what I was thinking is, well, if I could solve for A, then I could come back and put that A in that equation, and then solve for D. Once again, I'm going to I'm going to use the second equation right here, but I don't know A. So if I could put A in here, then I could solve for D and actually end up with an answer. Well, I do know a formula that's really, really easy for A, and that is delta V over delta T. And you see how I know both velocities and the time? So let's do that. Let's solve for A first. A equals delta V over T. Sorry about my hand on it. And so I'm going to say final 30 minus 20, final minus initial, divided by the change in time, which was 10. So 30 minus 20 is 10, divided by 10 is 1 meter per second squared. And now I can take this and put it back in that second equation. So let's use the second equation now. D equals VOT plus 1/2 AT squared. So D equals, the original velocity was 20 meters per second. The time that this thing goes is 10 seconds. Plus 1/2. The acceleration is 1 meter per second squared. And the time that it goes is 10. And that gets squared. So let's see what we get here. 20 times 10 is 200. And the seconds here, it's out the seconds there, so that gives me 200 meters. Plus, let's see, 1 times 10 is 10, half of 10 is 5. And, I just did a boo-boo. Hold on here. I got to do that 10 squared. So 10 squared is 100. Half of 100 is 50. And since this seconds gets squared, it cancels out with this second squared. So that second squared and that second squared go away. And I'm left with 50 meters. You add those two things together, and your answer ends up being 250 meters. So those are going to be the more challenging problems, is when you got to use more than one formula. And AP, you're just going to have to get used to it, because you might be using 3 and 4 at the same time. So let's take a look at one more thing here on the motion calculations problems, and that is number 4. Number 4. On number 4, it says you ride a bike for 1.5 hours, and so they give you a time of 1.5 hours. And they say that you're going 10 kilometers per hour, so your original speed's 10 kilometers per hour. And then they tell you, you then ride a bike for 30 minutes. Well, I got to keep all my units in the same, so I'm going to keep that as 30 minutes, the same thing as a half hour. And then you're doing that at a speed of 15 kilometers per hour. And it tells you to find out, what was your average velocity? Well, this sort of stinks, because you're going 2 different speeds. So I want you to remember what the formula for average velocity was. It was total distance over the total time. Well, the total time is sort of easy to figure out. You just add time number 1 and time number 2, and you bring that down. But if you notice, I wasn't given a distance. So you got to come back to that little triangle that I told you to remember. Remember, velocity equals distance over time? And if you wanted to find the distance, you can simply cover up that D, and it ends up being velocity times time. So look what you can do. You could find the first distance that you went, multiplying the time and the velocity together. You could do the second distance you went by multiplying the time and velocity together. And then if you add these two distances down here, you have to do like three different equations, but it's all the same formula. So that one's a little bit tricky there. So hopefully that helped you out with number 4. Have a great day. Hope you enjoyed it. Bye.